This section is about how to find the limit to an exponential function. The limit of e to the x power, the natural number e to the x power, is quite fascinating because the derivative, I should say, of e to the x power is actually itself. E to the x's derivative is just e to the x. This could be quickly proven by using the limit process, so doing the limit as h approaches 0 of e to the x plus h power minus e to the x divided by h. Remember that e to the x plus h is found by taking e to the x times e to the h. Remember, when you multiply with the same bases, you just add the exponents, so I'm doing that in reverse. Then we can factor out an e to the x power, so you have e to the x times e to the h minus 1 over h. And even though we still can't do a direct substitution, by the time you look at this portion on a graphing utility, you can see that it is approaching 0. And so you're left, or excuse me, approaching 1. So you're left with just e to the x times 1, which is just e to the x power. So e to the x is its own derivative. Derivative of a to the x is found by taking ln, the natural log of the number or variable a, times a to the x power times itself. The derivative of a to the g to the x power, let's say you have a base to a power that is something other than an x. It's its own function. So then you would take the natural log of the base times a to the whatever that power is, the exact same thing as the original function, times the derivative of the exponent, the g to the x portion of it. That is almost like a chain rule. And you can do that with a natural number too, so at e to the gx power, since the natural log of e is 1, that's why that portion appears to be cut out of it. It's just going to be e to the gx power, whatever the original function is, times the derivative of g to the x. So a couple of examples here. We get example 1a, and all of these are taken directly from your textbook. If you have y equal to e to the 5x power, and we're going to find the derivatives of these. So the derivative, dy over dx, would equal, this is going to be this equation formula right there. So it's going to be just e to the 5x power, the exact same value of the function, times the derivative of the exponent, which is 5. And I could simplify that by just saying that it is going to be 5e to the 5x power. Example 1b is s equals 3 to the t power. So we don't have the e. It's not e to some power. It is some number other than e to that power. So the derivative is going to be derivative of s in respect to t will be using this one right here. So it's going to be the ln of 3. So ds over dt, accidentally deleted that, be the ln of 3 times the 3 to the t power. And there's really not a whole lot of ways we can simplify that, so it's just going to be ln of 3 times 3 to the t power. And that's really all we can do with that. 1c is y equals 10e to the 3x squared power. So 10e to the 3x squared power. So that now we're back to using e. So it's going to be this formula right here. Now the 10 is a constant, so we're just going to be taking the derivative of e to the 3x squared power and then taking that times 10. So it'll be dy over dx will equal 10 times, and then we're just doing the e to the 3x squared powers derivative. So that will be just e to the 3x squared times the derivative of 3x squared, which is 6x. And then to simplify that, we can take 10 times 6x. That would be 60x, and then e to the 3x squared, which looks kind of funny. Realize that the first time you're looking at it, but that would be the exact function we could use in order to find instantaneous slopes, instantaneous ranges of changes, or anything that we might need to know using the natural number e. Example 1D is s equals 8 times 10 to the 1 over t power. So to find its derivative, it'll be ds over dt equals 8, the constant 8, times the derivative of 10 over 1 over t. So since that is a different base, it's going to be this one right there. So it's going to be the ln of 10 times the function 10 to the 1 over t power, that's the original function, times the derivative of the exponent, 1 over t. Well, the derivative of 1 over t, if I rewrite that as t to the negative 1 power, its derivative would be negative 1t to the negative 2 power, which could be rewritten as negative 1 over t squared. So that's the derivative of 1 over t. So negative 1 over t squared. We need to simplify that as much as we can. So it's all multiplication, so we will have just a t squared on the bottom. And then on the top, really about the only thing I can do here is I can take the negative 1 times 8. So that would be negative 8. And then I've got the ln of 10. Put it in parentheses to separate it from everything else, times 10 to the 1 over t power. And that is actually as simplified as it can get. So all of those were part of example 1A through 1B. Example number 2 is y equals e to the x squared plus 1 times 5x plus 2. So we're going to treat this as a multiplication rule. The first function being e to the x squared plus 1, and the second function being the square root of 5x plus 2. So this is going to be a product rule. So the way to find the derivative using the product rule is going to be the first function as it's written, so e to the x squared plus 1, times the derivative of the square root of 5x plus 2. So the derivative of the square root of 5x plus 2, we need to change that to 5x plus 2, the quantity, to the half power. So its derivative would be 1/2 times 5x plus 2 to the negative 1/2 power. And that would equal 1 over 2 times the square root of 5x plus 2 by the time I move that negative half power to the bottom and then revert it back to a square root. So times 1 over 2 square root of 5x plus 2. And that's just the first part of the product rule. Then we're going to add to that the second part of the product rule, and the second part is going to be the derivative of e to the x squared plus 1. So again, that is going to be the formula that is not circled. This one here exactly. So it's just the original function, e to the x squared plus 1, times the derivative of the exponent, x squared plus 1, which would be 2x. And then that's going to be times the second function, which is, I'm going to cross that out, the 5x plus 2. That way you're not confused where that came from. It's part of the stuff I put on the side. And that's the product rule. And we can definitely make this a little more elegant. So I can combine, I need to try to combine all this into a single fraction. So I'll start out by multiplying the first set, which is just going to be e to the x squared plus 1 over 2 times 5x plus 2. I'm going to add to that, multiply everything on the second one, which is actually, it's all going to be in the numerator. So it would be 2x e to the x squared plus 1 times 5x plus 2. So basically, since it's all multiplication, I just reorganized it. Well, if I'm going to add those together, I'm going to need a common denominator. So the common denominator is going to be that 2 square root of 5x plus 2, since it is the only denominator. So that is my only denominator. So 2 square root of 5x plus 2. That means I need to take the second portion of this, all of this, times 2 to the square root of 5x plus 2. So I'll have the e to the x squared plus 1 plus, and then I've got to do some multiplication here. So the 2 that I got in blue times the 2 that's at the start, that could just be 4. So I'm going to cross those out since I've already used that. And then I'm going to have the x e to the x squared plus 1. And then I do have square root of 5x plus 2 times the square root of 5x plus 2, and that's actually going to be 5x plus 2. Like that. All over 2 times the square root of 5x plus 2. And then there we get interesting here, because we have e to the x squared plus 1 in the first term, and then we have an e to the x squared plus 1 in the second term. So in order to make this a little more elegant, what we can do is we can factor out e to the x squared plus 1 from both of those terms. So e to the x squared plus 1 times, well, I factored out an e to the x squared plus 1 from this term, which means I'm left with just 1 plus 4x, and I already factored out this e to the x squared plus 1, so it's not there anymore, times the quantity of 5x plus 2. And again, all of that is over 2 to the square root of 5x plus 2. And then I can simplify that a little bit further. So I have e to the x squared plus 1, and I can simplify that by distributing the 4x into the 5x plus 2. So that will be plus 20x squared plus 8x. All of that is over 2 to the square root of 5x plus 2. And if I reorganize that into descending order of exponents, which is often done, that would be e to the x squared plus 1 times 20x squared plus 8x plus 1 over 2 to the square root of 5x plus 2. So if we're just finding just the derivative, that's the way we would need to do it. Since we had e to the x squared plus 1 in two different terms, I factored that out. Now, if we get into a situation where you just have to find instantaneous rate of change, maybe you don't want to go to the most elegant form. You can plug in whatever value you're trying to plug in for x at any time, and it will give you the instantaneous rate of change.